Shallow carbonate-dominated depositional environments come in two main categories, carbonate ramps and carbonate platforms. Although carbonate ramps are rare today, the Persian Gulf is probably one of the only good examples, one of the best studied examples as well. We're going to start with them because they share a lot in common with the siliciclastic shelves that you're familiar with from previous lectures. So what is a carbonate ramp? Well, it's basically just a gently sloping surface, hence the name ramp, that has a fairly consistent gradient from the shoreline to the deeper parts of the basin. Sometimes the gradient gets a little bit steeper at the offshore end of the ramp, and then it's called a distally steepened ramp. So this geometry is fairly similar to clastic shelves, like the shore face and offshore transition and offshore that you've heard about. So the distribution of energy is also pretty similar. Distal and deeper parts of the ramp have the lowest energy, and energy increases to a maximum in the shallow nearshore environment where the waves are breaking. Carbonate ramps are subdivided into environments using fair weather and storm wave base as boundaries. So those are the same boundaries used in siliciclastic shelves, but the environments unfortunately are given different names in the carbonate system. So the shallowest environment, the one above fair weather wave base but below the low tide line, is called the shallow subtidal. Between fair weather and storm wave base is the deep subtidal environment, and the offshore environment is the area below storm wave base. These are sometimes also called inner, mid, and outer ramp environments, but we'll stick with the shallow subtidal, deep subtidal, and offshore for our purposes. So just as a reminder, here's how they equate with the names given to similar regions on a siliciclastic shelf. So we'll start in the deepest water environments and work up to the peritidal side of things. So the deeper water environments on carbonate ramps have pretty similar facies to their siliciclastic equivalents, just with limestones instead of sandstones and shales. There are thin, coarser-grained storm beds, or these tempestites, possibly with HCS or maybe normal grading, gutter casts, etc. And they're interspersed with finer-grained sediments like lime mudstone or even siliciclastic mud. So as I mentioned in the last video, the rate of carbonate sediment production decreases as the water depth gets deeper. So in these really deeper water environments below storm wave base, the mud may have a lot of clastic, or also called terrigenous, clay in it just because carbonate production rates are very low. The shallow subtidal environment, which is above fair weather wave base, has a variety of facies depending on the conditions on the ramp, whether it's storm dominated or not, whether there's substantial tides or not, just not too dissimilar from siliciclastics. But one thing that you do tend to find on a lot of carbonate ramps that is not so common on clastic shelves are these shoals, which are basically large sandbars or dunes made of, say, ooids or skeletal fragments. Subaqueous dunes like this do occur on clastic coastlines. You may remember we talked about the longshore-dominated dunes that you can sometimes see in the shore face environment of clastic coasts. But they're not common there, and they end up being much more common or widespread in carbonate environments. So because these shoals are large dunes, they generate large-scale crossbedding. On the picture on the right, the scale bar is difficult to see. You might be able to pick it out in the middle there. But these crossbeds are around 60 centimeters thick, so very large dunes made of carbonate, say, packstone or grainstone. So shoals and the resulting dune crossbedding are fairly common, but other more typical shore face sedimentary structures like wave ripples, swaly cross stratification, low-angle beach laminations may also occur. In the case of the beach rocks, because the beds are lithified on or near the seafloor, they may develop these hard grounds. They're lithified hard rock on the seafloor, and so what you might see in them are borings of the Triponites ichnofacies, these little boreholes that form in lithified rock. So I want to spend the remainder of this video introducing characteristic facies of peritidal carbonates. Peritidal just means near tidal, and it refers to the shallowest part of the carbonate ramp. It includes the subtidal, which is sort of consistently at or below the low tide line, the intertidal between low and high tide marks, and the supratidal, which is consistently above the high tide line, except maybe during unusual storm surges or other sorts of events. Peritidal facies are generally pretty recognizable in outcrop. They're typically light gray or light brown limestones, or often dollostones. Usually they're lime mudstone or very fine grained. They have these thin, crinkly or wavy laminations that probably represent the wrinkled surface of microbial mats growing on the tidal flat. There may be these millimeter scale oval-shaped voids, possibly filled with calcite spar, which are called fenestrae, which is the Latin word for window. They're little tiny windows in the rock, these clear calcite ovals. So fenestrae form when gas bubbles from decaying organic matter or other sources gets trapped beneath the microbial mats. It creates a small void space that will eventually, or may eventually, get filled in with calcite during burial of the rock. So peritidal settings, the intertidal and sometimes the supertidal, are places of intermittent wetting and drying of the sediment as the tide rises and falls. So because of that, sedimentary structures associated with desiccation, or drying out, are extremely indicative of peritidal deposition. So the most common of those would be these polygonal networks of desiccation cracks, sometimes called mud cracks. You see them in a lot of sort of drying up water bodies, small like lake beds. If you go to Death Valley, you see desiccation cracks all the time. They just reflect wetting and drying of the sediment. So continued wetting and drying of these desiccation cracks can deform the laminations upwards into this V shape, which forms a sedimentary structure called a teepee structure. They are also pretty indicative of the supertidal and intertidal zones on these carbonate tidal flats. And if this process continues to an extreme, the teepee may grow really large and get disrupted, either just by continual cycles of desiccation or by these occasional storm waves that will come in and break up the lithified sediment. And so this forms a deposit called a flat pebble conglomerate. So as the name suggests, it's just a bed composed of broken up tabular pieces, generally quite long and thin, sort of square, blocky pieces of the underlying unit. So the name is somewhat inaccurate because the pieces are typically quite angular blocks, and so it should really be called a breccia, but the name flat pebble conglomerate is just what's used. So one important note of caution: flat pebble conglomerates just form when thin layers of limestone get lithified on or just below the seafloor, and then those thin layers get ripped up and moved around by storm waves. So they're not restricted to peritidal settings, and in fact, they can be fairly common in shallow subtidal environments, at least before the Ordovician. The reason for this is that bioturbation levels, or the amount of sediment mixing by organisms, were typically low in the Cambrian, and there was really no sediment mixing before the Cambrian. So this means that very thin layers of limestone could be deposited, preserved, and lithified then. When bioturbation is more common and more intense, a thin layer of deposited sediment just gets homogenized and mixed up. And so this means that only thick beds can be preserved, and thick layers just can't be ripped up and redistributed by storms. So in this case, the flat pebble conglomerates basically disappear in normal marine environments after the Cambrian Ordovician, although they're still found in sort of beach and tidal flat environments. Sometimes the supertidal part of a tidal flat can be very evaporative. In arid environments, the supertidal flats are given a special name, this name called a sabkha. It's after the Arabic word for salt flat. So a sabkha is characterized by high levels of evaporation, so that means that evaporite minerals, like gypsum or anhydrite or possibly even halite, might form. In many cases, the original mineral has been dissolved and has been replaced by calcite or something like that. The crystal void has been filled up by calcite. And so the characteristic shape might still be preserved, like in the left-hand photo shows these characteristic lath or blade-shaped gypsum crystals. So when a crystal retains the shape of the original mineral, but has a new chemical composition, it's called a pseudomorph. So the left-hand photo shows calcite crystals that are pseudomorphs after gypsum. So that pretty much concludes the characteristic features of carbonate ramp facies. The next video will discuss carbonate platforms, which are the classic and the best studied of the carbonate environments. Many of the facies and structures that we discussed today are also found in carbonate platforms, but the distribution of energy differs significantly, and so this means the distribution of facies is also very different.